What if your irrigation valve stopped working today? How would you know whether the problem was a mechanical or electrical? Most irrigation valve failures fall into just two categories. The valve will open or the valve won't close. But the cause of those failures can be very different. And guessing your way through repairs wastes time, money, and sometimes the customer's patience. I'm Dr. Denise DeBusk, and in this section, we'll learn a systematic step-by-step troubleshooting process that quickly identifies whether the valve problem is mechanical, and if so, how to diagnose it efficiently. You'll see that successful troubleshooting isn't guesswork, it's understanding how a diaphragm valve works, what conditions must exist for it to open or close, and how to apply simple tests in the correct order. By the end, you will be able to determine why a valve failed and what to fix first before replacing parts unnecessarily. Before we can fix any valve problem, we must ask the most important question in troubleshooting. Is this an electrical failure or a mechanical failure? Many technicians waste time by starting at the controller and working backward through electrical testing. That approach only works if they get lucky, and the issue turns out to be electrical. A faster, more logical path is to run two simple tests that immediately tell you which type of troubleshooting to pursue. Test number 1. The valve won't close, it's stuck on. Unplug or shut off power to the controller. If the valve closes, you know electricity was the reason it stayed on. Electrical problem. If the valve stays on, electricity is no longer present, so it must be mechanical. Test number 2. The valve won't open. Try opening it manually at the valve. If it opens manually, the valve works hydraulically, so the failure is electrical. If it won't open manually, something is physically preventing movement. Mechanical problem. Once we identify it as mechanical, we know what to look for. Mechanical issues always fall into one of these categories. Something is clogged, something is leaking, something that should move is stuck, something that shouldn't move is moving, or something is broken, cracked, or torn. Finally, always remember, a diaphragm valve opens and closes hydraulically. Electricity only initiates the process. The diaphragm moves because of water pressure changes above and below it, and that principle guides all mechanical troubleshooting. Before we go any deeper into troubleshooting, we have to anchor everything to how a diaphragm valve actually opens and closes. The solenoid only starts the process when it receives power from the controller, but after that, the valve's movement is completely driven by hydraulics. In the closed position, the pressure on top of the diaphragm is greater than the upward force under it, so the diaphragm stays sealed. To open the valve, the system must reduce the pressure on top, allowing the higher pressure underneath to push the diaphragm up. To close the valve again, pressure is rebuilt on top so it becomes greater once more. The key takeaway for you as a technician is this: if the valve can't build or release pressure above the diaphragm, it cannot open or close properly. So every mechanical troubleshooting step ultimately ties back to this hydraulic principle. To open a diaphragm valve, the water on top of the diaphragm has to be released so the diaphragm can lift. Electricity starts the process, but hydraulics actually do the lifting. 4 things must happen every single time. The valve must have water. The solenoid has to open its exhaust port. That water must flow off the diaphragm, and then the diaphragm can rise. If even one of these steps fail, the valve will stay closed. This simple sequence is the foundation for troubleshooting a valve that won't open. When a valve won't open, I always begin with one simple test. I manually operate the valve. No matter what a customer says, no matter what I think might be wrong, this step cannot be skipped. I turn the solenoid a quarter turn to simulate what the solenoid would do electrically. If the valve opens manually, then hydraulically the valve is working just fine, which means I'm dealing with an electrical problem and I should go troubleshoot the controller or the circuit. But if the valve doesn't open, then I've immediately confirmed it's a mechanical problem and I can move on to step 2. Now, one side note, this method doesn't test whether the plunger inside the solenoid is stuck, but that's actually pretty rare with modern valves unless the water source has a high iron content. For the vast majority of cases, this quick test points us in the right direction without wasting time. For a valve to open, it has to have water. And this is one of those simple steps that techs often overlook in the rush to fix the valve. A valve can operate electrically with no water present, but we can't see or confirm anything unless water actually reaches the sprinklers. So in this step, we pause and ask a very basic troubleshooting question. What is preventing water from getting to this valve? The first thing I do is turn on other valves. If all other zones work, then the issue is isolated to just this valve. If none of the zones are working, then something is shut off farther upstream, which means this isn't a valve problem at all. Common issues include closed valves at the meter, backflow, pump, mainline, or manifold. It could also be a pump that's off at the breaker, reclaimed water on a restricted schedule, a closed flow control holding the diaphragm shut, or a clogged mainline filter, especially on reclaimed or surface water systems. Once I know water is definitely reaching the valve, then I can move on to step 3. Step 3 is all about the solenoid. The solenoid's plunger has to lift to open the exhaust port so the water can leave the top of the diaphragm. If that plunger can't move freely, the valve will never open, even if everything else in the system is perfect. First, I remove the solenoid, making sure the water is off. If the solenoid was extremely tight, it may have been over-tightened to the point that the plunger couldn't lift high enough. In that case, always check the O-ring to make sure it's not crushed or cut. Then I test the plunger by pressing it with a paper clip. It should move smoothly against spring tension. If it sticks, binds, or barely moves, the solenoid is the problem. If it moves freely, I reinstall it and manually test the valve again. Only if it still doesn't open do I move on and replace the solenoid. The key here is to confirm the problem instead of guessing and replacing parts at random. This step prevents wasted time, wasted solenoids, and confusion during troubleshooting. To open a diaphragm valve, water must be able to escape from the bonnet area. If that water can't flow through the exhaust ports, the pressure never drops and the diaphragm can't lift. At this stage, I ask myself one question. What is preventing the water from leaving the bonnet? The fix is often simple and mechanical. I'll start by turning off the water, removing the solenoid, and using a paper clip to clear both exhaust ports, one in the bonnet and one under the solenoid. A common culprit is PVC cement or debris that hardened inside the port. After clearing it, I briefly turn the water back on to flush the ports, reinstall the solenoid, and try opening the valve again. If the valve now opens manually, we've solved the issue. If not, it's time to move to step 5. Now that we've confirmed the solenoid and exhaust ports are not the issue, the final possibility is that the diaphragm itself is unable to lift off the seat. If it can't move freely, the valve will never open fully. I start by shutting off the water, removing the bonnet, and pulling out the diaphragm. Sometimes it's literally stuck to the seat from organics drying out in the water. In that case, I just clean it and move on. If you're dealing with a reverse flow valve, also check for holes or tears, because that can stop the pressure on top from releasing. The key question I'm asking is, what is physically preventing this diaphragm from lifting? If the diaphragm itself looks good, then I move to the metering pin and port. Over many years, that port can wear out and go out of round, which keeps too much water on top of the diaphragm. And because water doesn't compress, the diaphragm won't lift. In that case, I replace the pin or bonnet, flush the valve, reassemble, and test again. My final step is always a manual test. If the valve opens, I'm done. If not, I flush and repeat. This step is all about eliminating mechanical resistance. When a valve won't close, our goal is to figure out why the diaphragm can't reseat and hold water back. Remember, closing a valve is the opposite of opening one. Instead of relieving pressure on top of the diaphragm, we must build pressure on top of it. There are 4 conditions that must be met for a valve to close properly. The water must stop exiting the bonnet must fill, the diaphragm must move down and fully seat on the valve body, and that pressure on top has to remain higher than the force underneath. If any one of those 4 conditions fail, the valve will stay on, run continuously, or close extremely slowly. In the next steps, we'll walk through a fast and efficient troubleshooting process that isolates the mechanical cause without wasting time or replacing the wrong parts. Before touching the valve, we need to confirm what type of problem we're dealing with. Fastest way to do that is to disconnect the power at the controller in step 1. If the valve closes when the power is removed, then we know the controller or wiring is holding the valve open. That's an electrical issue. But if the valve stays on even with the power shut off, the valve is being held open mechanically. And that means we need to troubleshoot the internal hydraulics. This step cannot be skipped. Doing it first prevents us from wasting time digging up valves that don't need to be dug up. Now that we know that the problem is mechanical, our next job is to make sure water isn't escaping from above the diaphragm in step 2. If water continues to exit through the exhaust ports or a bad seal, the valve cannot build pressure and it will never close. First, confirm the manual bleed and solenoid are fully off and tightened. Next, check for leaks between the bonnet and valve body. Even a small leak will prevent the valve from sealing. The common cause for this type of leak is one or more of the screws have been cross-threaded into the plastic valve body instead of threading into the previously cut threads, like a bolt into a nut. Then remove the solenoid and look for debris around the plunger seat. If something is preventing the plunger from sitting tightly over the exhaust port, water will keep escaping and the valve will stay open. You can use a paper clip to check if the plunger is moving freely. Once we eliminate these escape points, the valve should be able to build pressure and move toward a closed position. To close the valve, we now need the bonnet, the space above the diaphragm, to fill with water so pressure can push the diaphragm back down. If that area fills too slowly, the valve will close slowly. If it doesn't fill at all, the valve won't close at all. So first I ask in step 3, is this valve simply too big for the flow? A valve that's oversized won't build enough pressure in the bonnet. Check the manufacturer's pressure loss chart, compare it to the actual flow of the zone, and see whether the valve has enough pressure loss to function properly. Here's an example on the slide. If the pressure loss is under 3 psi, you can fine-tune the flow control. A simple adjustment: fully close it, open it 2 turns, and then adjust for proper throw, can reduce the bonnet volume and allow the valve to close faster. If adjusting flow control doesn't solve the problem, I move on to the next most likely cause: air or internal blockage. Trapped air in the bonnet is extremely common after repairs, winterization, or long shutdowns. Bleeding the air through the bleed screw or by loosening the solenoid allows water to replace the air so pressure can build. If that isn't the issue, I open the valve and inspect the internals. I make sure the spring is installed, check for diaphragm tears, and look for clogged diaphragm ports or filters. Since water must travel through these pathways to close the valve, any blockage will cause slow or failed closing. After flushing and reinstalling or replacing parts, I test the valve again. Now that we know the valve can build pressure, in step 4 we need to make sure the diaphragm can actually move down and seal against the valve body. Even a small pebble or piece of grit can prevent a watertight seal. And because the diaphragm lifts only a short distance when the valve is open, debris often gets trapped beneath it. Many technicians open a valve, don't see anything obvious, and assume it's fine, only to miss material that rolled back into the pipe when the system was drained. My rule is simple. Anytime a valve is opened, it must be flushed before reassembly. Once debris is cleared and the valve has been flushed for 30 to 60 seconds, we can move on to step 5 and verify that the valve will stay fully sealed when it closes. A valve can be technically off but still leak if the diaphragm isn't sealing properly. We call this a weeping valve, and it often goes unnoticed because you might not actually see water flowing. Instead, you look for the clues: algae along a curb, a constantly soggy spot by the lowest sprinkler, or a customer complaining about unusually high water bills. For step 5, once the valve is open for inspection, always start by looking at the bottom of the diaphragm. Even tiny cuts, dents, or embedded debris can keep it from sealing. If the diaphragm is clean, the next suspect is the diaphragm seat in the valve body. You can run a fingernail around the full edge to check for nicks or chips. If the seat is in good shape, flush the valve, reassemble it, and test it again manually. The goal is simple: a tight seal with zero seepage. Before moving on, let's summarize the big picture. When a diaphragm valve won't open, something is preventing the pressure on top of the diaphragm from being released. That's why we manually open first, check for water, verify solenoid movement, and make sure the diaphragm can lift. When a valve won't close, something is preventing pressure from building on top of that diaphragm. So we begin by removing electrical influence, making sure water isn't escaping the bonnet, and confirming the diaphragm can seat tightly. In every case, troubleshooting comes back to one core idea: to open, relieve pressure; to close, build pressure. If you remember that, the step-by-step process becomes very logical. In this last section, I'll talk about indexing valves. Indexing valves behave very differently from diaphragm valves. Instead of opening and closing to start or stop water, an indexing valve is more like a traffic director. It sends water to one zone at a time in sequence. When the pump or master valve turns on, water pushes a disc down to supply a specific outlet. When the water turns off, the drop in pressure lets that disc lift and rotate part way. Then when the flow starts again, it completes the movement to the next outlet. That's where the name indexing comes from. Because the valve depends entirely on the stop and start flow cycle, most troubleshooting focuses on making sure the disc can move freely, the outlets aren't blocked, and the system is providing enough flow and delay between cycles. In the next slides, we'll look at the three most common symptoms and how to fix them step by step. If an indexing valve doesn't advance to the next zone, it means the stem and disc aren't able to reset when the flow shuts off. The first thing to verify is that there is a delay between cycles, ideally around 15 minutes. Without that pause, a valve never has time to lift and rotate. Next, check for debris in the cam or disc assembly. Even a grain of sand or scale can jam that movement. If fewer outlets are being used than the valve is designed for, a misset cam is another frequent cause. The cam holds the disc in the position, and if it isn't locked in correctly, the disc won't index. Finally, look for outlet or backflow restrictions. This is especially common when the next zone runs uphill. Back pressure can't hold the disc down and prevent it from advancing. Work through these in order, and you'll solve most not advancing complaints without taking the whole valve apart. When water comes out of every outlet at once, the indexing valve isn't sealing the disc against the individual outlet ports. In most cases, the root cause is low flow. Indexing valves require a minimum flow, typically 10 gallons per minute, to push the disc down and seal off the other outlets. If the system is below that threshold, you'll see weak flow everywhere instead of strong flow on just one zone. Debris under the disc can also prevent a tight seal. So removing the valve top and checking for sand, scale, or obstructions is the next step. It's also important to verify that the correct stem and disc assembly is installed for the flow range. Using a low flow disc on a high flow system or vice versa will cause sealing issues. Finally, check downstream for restrictions or check valves that can trap pressure and hold the disc off its seat. Once flow is adequate and the disc can seat cleanly, the valve will isolate each zone properly again. When an indexing valve skips a zone, the first place to look is the installation. Indexing valves don't send water to every port by default. The cam determines which outlets are active. If the wrong cam is installed, or if a lateral was connected to an outlet the cam is designed to skip, that zone will never run. It's also important to verify that each outlet pipe matches the numbered ports shown on top of the valve. A single mismatch can make it look like the valve is stuck or skipping ahead. Once the installation issues are ruled out, then look at hydraulics. A pump that loses prime or a bouncing check valve can cause sudden surges in flow, which advances the disc too quickly and causes the valve to jump past a zone. Stabilizing flow or repairing the check valve usually resolves the issue. With the correct cam, proper outlet connections, and steady flow, the indexing valve should advance one zone at a time every time. With indexing valves, everything comes back to flow and movement of the stem and disc assembly. If it won't advance, won't seal, or skips, your troubleshooting focuses on debris, cam setup, and stable flow from the pump or master valve. Once you understand how it sequences, diagnosing problems becomes extremely predictable.